Okay, so now I want to introduce simple collision theory. Okay, so if we have, I don't know, H reacting with O2, okay, what's the best geometry of approach of the hydrogen atom with O2? Okay, what is the most efficient way of supplying energy to overcome the activation energy barrier that's involved in the reaction? Okay, what are the rates of movement around the reaction coordinate? How is the energy distributed among the products of reaction? Okay, these are some of the questions that we need to consider if we're thinking of the reaction coordinate. Okay, and it's similar to the diagram that I showed you earlier that was a video. Okay, so again, if for simple collision theory, we consider the species like hard spheres. Okay, and if we have a low concentration, we'll have few collisions. If we have high concentration, we'll have more collisions, right? But we consider the molecules as hard structureless spheres like billiard balls. And we assume that there are no interactions between them until they come into contact with one another. And then and that they are impenetrable, they maintain their size and shape, and they cannot come closer than the radii from one another, okay? And so we assume that the molecules are hard spheres and every collision is reactive, okay? So if we do that, okay, and here we have H reacting, we'd say, with O, okay, we have the radius of A and we have the radius of B, and their reaction together. So if we calculate the rate of collision, that will give us the rate of reaction, okay, assuming that molecules are hard spheres and every collision is reactive. So in 1 second, a typical A travels a distance d is equal to nu A times t, okay, which is, and will collide, with all B's within collision cylinder of volume pi RA plus RB squared times nu A, meters cubed, okay? So the distance is equal to, we'd say, the velocity of A times t. Okay. So NB times pi times RA plus RB squared times nu A, single collisions of A with B per second will occur, right? And that's the collision frequency is ZA, okay? But the total collision rate is ZAB between A and B is equal to the number of moles of A times the number of moles of B times pi times RA plus RB squared times nu AB, okay? Which is the rate or the speed at which both species are traveling. But this is in 1 second. It's per meter cube per second, okay? And that's why we can take nu A. So the distance is nu A times t, but because t is 1, then the distance is nu A, the velocity, okay? So the reaction rate is equal to K2 times nu A, the number of moles of A times the number of moles of B, okay? And the collision rate is equal to pi times RA plus RB squared times nu AB times the number of moles of A times the number of moles of B, okay? So reaction rate, I said earlier, if we have A and B, it's the concentration of A times the concentration of B. The reason we can use concentration is if we have unit volume, okay? So if volume is 1, we can use concentration. But actually, the proper definition of rate of reaction is the number of moles of each reactant, not concentration of each reactant, okay? So in this case, it's K2 times the number of moles of A times the number of moles of B. So if we have, this is the reaction rate and this is the collision rate, then we can say, okay, the rate constant is then equal to pi RA plus RB squared times nu AB. And that's equal to the collision cross-section AB times the velocity AB, nu AB. So where do we get nu AB from? And that comes from the Maxwell-Boltzmann distribution of velocity. Okay, so nu AB is defined as equal to the square root of AKT all over pi mu. Okay, so the rate at which A and B collide, that's speed, is directly proportional to temperature and inversely proportional to the reduced mass. So the heavier they are, the slower they'll be traveling, okay? And the higher the temperature, the faster they'll be traveling, which makes sense, okay? And the collision cross-section, sigma AB, is equal to pi RA plus RB squared, okay? The collision cross-section, okay? So in practical units, nu AB is equal to 4.602 times T times the relative molecular mass of A plus the relative molecular mass of B divided by the relative molecular mass of A times that of B, and it's the square root of that term, okay? And that's where mx is given in kilograms per mole and T in Kelvin, okay? So actually, you can sort of interchange these as long as you can use, this is on a per molecule basis, you use K, on a molar basis, you use R in this equation. And I'll talk about that in a few minutes, okay, on the next slide probably. Okay, so here we are. Calculate the mean time between collisions experienced by a single argon atom at 300 Kelvin and atmospheric pressure, right? The collision diameter for argon is 0.29 nanometers, and the relative molecular mass is 0.04 kilograms per mole, okay? So the cross-section, collision cross-section is pi RA plus RB squared, okay? But it's argon colliding with itself, so in other words, it's the diameter of argon, okay? So the collision diameter is 0.29 nanometers, so this is going to be pi times 0.29 nanometers, and that's 2.64 times 10 to the minus 19 meters squared. Yeah. Give me a minute. Okay. Okay. We'll get there. Okay. So, and then we have nu AA. How do we get that? That's the square root of AKT over pi mu. Okay? The square root of AKT over pi mu. So I've shown the calculation here and I've shown the calculation here. Do it yourselves and see that you get the same number as me. Okay? So that you prove that you can, to yourself that you can do it. Okay? Not to me. So here, so even at this low temperature and atmospheric pressure, well, 300 Kelvin and atmospheric pressure, argon atoms are moving at twice the speed of sound. Okay? Well, or almost that. It's 563.67. Okay? But we know PV is equal to nRT, so the number of moles is equal to N divided by the volume, and that's equal to P over RT. So we have 101,325 divided by 8.314 times 300. Okay, so the number of moles of argon is 40.1 moles per meter cubed, and that's 2.4 times 10 to the 25 molecules per meter cubed. Okay, so that's okay. So the collision cross section, or the collision frequency, is equal to Na times sigma AA times nu AA. And that comes out to be equal to 3.57 times 10 to the 9 molecules per second. Okay, so this is the collision frequency. So the average time between collision is the inverse of that. It's 1 over the collision frequency, and that's 280 picoseconds. Okay, so the average time between collision of argon atoms at 300 Kelvin and 1 atmosphere is 280 picoseconds. Okay, so it's kind of a nice calculation. So let's test simple collision theory. Okay, so we have methyl plus methyl giving us C2H6. The relative molecular mass of a methyl group is 0.015 kilograms per mole. We're at 300 Kelvin, and the diameter is 0.308 nanometers. Okay, so the rate constant is equal to the sigma AA times nu AA and that's 2.98 times 10 to the minus 19 times 920.25. And that comes out to be equal to 2.745 times 10 to the minus 16 meters cubed per molecule per second. Okay, so if I convert that to centimeters cubed per mole per second, it comes out to be 1.65 times 10 to the 14 centimeters cubed per mole per second. Experimentally, it's calculated to be 2.4 times 10 to the 13, right? So, and actually, this is a unique result. It's unusual that we're even this close, right? So this is within an order of magnitude, you could say. It's about a factor of 10. A bit less, but let's just say it's factor of 10. Normally, the calculation would be way, way better than experiment, or bigger than experiment. And your name, I can't remember. Patricia, yeah. So as Patricia was saying, we're assuming that every collision is reactive. Actually, there's an efficiency factor. And so, in this case, the efficiency is about 0.1. Okay, so the efficiency factor is coming out to be about 0.1. So only 1 in 10 collisions are reactive in reality. That's what experiment is telling us. And hence, the experimental value is 2.4 times 10 to the 13. We're assuming it's perfect, and it's 1.65 times 10 to the 14. But to be within a factor, an order of magnitude, is unusual. Okay, normally we're way out. Okay, so then it calls into question: is simple collision theory worth it at all, or does it do anything? Okay, and so but the reason that we're way out is that we didn't include any temperature dependence. Okay, and we need to. Okay, so how do we improve this? Okay, so we have to think of this a critical energy for collision. Okay, and so this is just the fraction of species involved in reaction. Okay, and we say, okay, if the energy, okay, is lower than the critical energy, so the energy collision, the energy for collision is greater than or equal to the critical energy, then the reaction occurs. Otherwise not. Okay? So, in other words, if you don't have enough energy to get over the critical energy, then no reaction occurs. If you do, then all reactions occur. It's all or nothing. Okay? And hence you have the zero arise, and then all reaction occurs. Okay? So if your energy is below the collision energy, no reaction occurs. But if it's equal to or greater than it, all reactions will occur. Okay. So now we can say, okay, well, this F, the fraction, is equal to the exponent of minus the critical energy all over kT. And so this is on a molecular basis. On a molar basis, that's equal to the exponent of minus capital EC all over RT. Okay, so this is on a per molecule or per atom. This is on a per mole. Okay, so now we have K2 is equal to sigma AB, nu AB, times the exponent of minus a critical energy all over RT. And so now we have K is equal to A e to the minus EA over RT. Okay, so it's very similar to our Arrhenius equation. Okay, so the frequency factor is the sigma AB times nu AB, which makes sense, except that we have to include this efficiency, as Patricia was saying, right? And normally, sometimes the efficiency can be even greater than 1, but most of the time it's less than 1, because not all reactions will be, not all collisions will be reactive. Or well, not all collisions will occur, should I say. Okay. So, and now the Ray constant will be much smaller, and we have a temperature dependence. Okay, and it should be better now because we have a critical energy all over RT. But how about the critical energy? The question is the critical energy, we have conventionally, Ray constant is equal to A e to the minus EA over RT. And now we have Ray constant is equal to sigma AB the square root of 8 RT over pi mu, this is on a molar basis, times the exponent of minus a critical energy over RT. Okay, so does EC equal EA is the question. And the answer, of course, is no, right? Because we have to do all of this down here, okay? So let's just look at it. We have, from this equation here, the change in log K, d log K, d 1 over T, okay? So the derivative of log K with respect to 1 over T is equal to minus EA over R, okay? If that's okay. So if we have log K is equal to log A minus EA over R times 1 over T, okay? So d log K, the derivative of log K with respect to 1 over T is minus EA over R, okay? And we have K2 is equal to sigma AB 8 RT pi mu, the square root of that times the exponent of minus the critical energy over RT. So let's just write it, that as equal to Y times T to the half times the exponent of the minus the critical energy over RT, just for argument's sake for now, okay? So we have log K is equal to half log T minus the critical energy over RT plus log Y, okay? Or log K is equal to minus a half log of 1 over T minus the critical energy over R times 1 over T plus the log of Y, okay? So again, the derivative of log K with respect to 1 over T then is equal to minus a half T minus the critical energy over R, okay? And this is then equal to, based on the Arrhenius equation, that's equal to minus EA over R, because that's what we got from the Arrhenius equation, okay? So EC is actually equal to EA minus RT all over 2, okay? So they're not actually equal. So we can actually write K2 is equal to sigma AB, nu AB, times the exponent of minus the critical energy over RT, and that's equal to sigma AB, nu AB, the exponent of minus the activation energy all over RT times e to the half, okay? So you have to include this times e to the half term to correct, okay? And now you can put in EA, okay? So that's the relationship between the two. Have a look at that yourself and derive it yourself. I kind of went quickly, but I think it's fairly clear. Most of you will be familiar with that. Okay. I'm going to talk for as long as we can all bear it and stick, okay? But if you really want me to stop, tell me to stop and I'll stop, right? But I'm going to talk about experimental facilities. So that's sort of my end of the theory, the kinetic theories and so on. That's as much as I'm going to do, right? Now I'm going to talk about using experimental facilities and the kinetics that are related to those, right? And I'll talk about jet-stirred reactors and flow reactors to start with. And if we get that done, I may go on and talk about shock shoes and RCMs, maybe not. I might put it off until tomorrow, okay? But anyway, so this is a slide that I got from Philippe Dagot many years ago now, and it's representation of his jet-stirred reactor in Orléans. And his group, it wasn't him, but Professor Castanet, I think, that started the jet-stirred reactor work in Orléans. And this is actually what it looks like in real life. It's quartz material. Here you have the inlet. You have the gas comes in. It goes into these 4 jets that are at right angles to one another so that the gas is very well mixed inside the reactor. And then the flow rate is such that there's a certain residence time for a reaction inside the reactor. And then the gas comes out the other end, okay? So you have, here's just a depiction of that. Here we have a thermocouple measuring the temperature at the center of the reactor, and you have a sampling probe taking samples of species from the center of the reactor, all right? So, and then so this is a close-up of the reactor itself. Here it is. Here we have the quartz reactor. It's inside this heating tube on either side, or heating on either side of it, and then it's inside this metal tube for protection. Why is it inside here, and why do we have this metal casing? Right? Okay. Yeah, so, yeah, but not just for safety, but definitely for safety, but also for practical to do higher pressure. So actually a lot of the experiments that he does are at 10 atmospheres. So for practical applications, atmospheric pressure isn't great. So to have data at 10 atmospheres is good, right? But to get to 10 atmospheres in a quartz reactor, you're going to, as you said, blow out the quartz, and it'll go in your eyes and might kill you, right? So it's not great. So exactly that. You have a gas inside here, and you just equilibrate the pressure on either side of the reactor, and you can do your experiments, okay? So that's the point. Okay, so then you have an atomizer, vaporizer. You vaporize your components so that when they come in here, they're well mixed. Well, they're well mixed in the reactor because the inlet, they're all at right angles to one another. So you've got good mixing of all the reactants inside the reactor. And then the flow rate determines the time. Okay, here are the type of results. So this is actually from experimental results from Olivier Herbinet, working with Frédéric Baron-Leclerc in Nancy. Okay, and these are data for N-heptane oxidation, taken at equivalence ratio of 1, a residence time in the reactor of 2 seconds. We'll come back to that in a minute. A pressure of 1 bar and 0.5% fuel. Okay, and what they've measured, I think about 26 different species here, right? So you have 3, 6, 9, 12, 15, 19, 20, 21, 22, 23, 24, 25, 28, 30 different species, okay? And so what they do is they do the experiments at 500 Kelvin, they measure the species concentrations, then they up the temperature by 25, 50, 75, 600, and so on. And they sweep temperature from 500 to 1100 Kelvin, recording the species concentrations as a function of temperature at this specific condition, okay? And then the points are the experimental results. The lines are model predictions of these data. So it's really valuable data to validate a model, to have these kind of speciation profiles, because it really tests the detailed chemistry. Are we reproducing the fuel and oxygen profiles correctly? Are we producing some of the ethylene, methane, propene, all these major intermediates correctly? If we're not, then our and we are getting ignition delay times right, our chemistry is getting the right answer for the wrong reasons, okay? And so having species profiles really helps in telling us whether the chemistry, the pathways are correct or not in our mechanisms, okay? So let me just, first of all, I alluded to this a minute ago, but I'll talk about it now, that we define the rate of reaction as 1 over the stoichiometric coefficient, the change in number of moles of a species with respect to time, not the change in concentration. But actually, you'll see in a second. So VI is the stoichiometric coefficient. It's positive for products and negative for reactants. So for example, if we have 2H2 plus O2 giving us 2H2O, what's this? The stoichiometric coefficient with respect to hydrogen is -2, oxygen is -1, and water is +2, okay? And so at constant volume, though, as I said, I alluded to this before, the concentration of A is equal to the number of moles per unit volume, or the number of moles is equal to volume times the concentration of A. Because we were assuming unit volume, then we could interchange moles and concentration, okay? But you shouldn't really do that. And the proper definition is moles, not concentration, when you come to kinetics. Okay? So you should write the change in number of moles of A with respect to time is equal to the volume times the change in concentration with respect to time. So you should actually include the volume in your definition. So the old rate of reaction was reaction rate per unit volume. Okay? So the change in concentration of A with respect to time is equal to 1 over volume times the change in number of moles with respect to time. Okay. Anyway, if you have unit volume, it's 1. So you can interchange them. Okay. So flow versus batch reactor then. So a stirred flow, perfectly mixed reactor. If we have a spherical shaped reactor, we can derive an equation that says if we measure the concentration of A at the outlet, that's equal to the concentration of A at the inlet divided by 1 plus the rate constant times the volume divided by the flow rate, nu. Okay? This is the volumetric flow rate, nu. Okay? We can derive that equation. For a flow reactor, a cylindrical flow reactor, we can derive this equation, which says the concentration of A at the outlet is equal to concentration of A at the inlet times the exponent of minus the rate constant times the volume divided by the volumetric flow rate. Okay? We can derive those, and we will. Okay? So remember, though, that actually the volume divided by the volumetric flow rate, divided by V divided by nu, is actually meters cubed divided by meters cubed per second, and that's seconds. Okay? So if you remembered a second ago, I had underneath Herbin et al., and then I gave the conditions. And it said, was it 1 second or 2 seconds? I forget. 2 seconds. What they actually had was the volume of the reactor, and then they had the volumetric flow rate. But they didn't provide that when they published the work. They already translated that into a residence time. So typically, people don't give you the volumetric flow rate and the volume. They just give you the time. Okay? But how they calculate the time is by that. So they know the volume of their reactor, and they're measuring the flow rate, okay, to get that time. Okay? So just bear that in mind. So here we have then the stirred reactor. Okay? And here we say, okay, the change minus the change in number of moles of A with respect to time is equal to the rate constant times the number of moles of A. So we have, in other words, the kinetics here is we have A reacting to give products. Okay? So, and that's equal to the rate constant times the volume of the reactor times the concentration of A. Okay? So we can write it as the rate constant times the number of moles of A, or the rate constant times the volume times the concentration of A. Okay. And so if we have the sphere, we have A going in, the sphere has a certain volume, and then we measure A at the outlet. Okay? So, but will the concentration of A at the outlet equal concentration of A at the inlet? Well, maybe, but if it is, then no reaction has occurred, and there's nothing interesting. Okay? Go home, right? Whereas, okay, if something happens, then we have inflow is equal to outflow plus some reaction. So something's happened. So that's good, right? So we have then assume the system is at constant volume so that the inlet flow rate is equal to the outlet flow rate. So we have the volumetric flow rate times the concentration of A at the inlet is equal to the volumetric flow rate times the concentration of A at the outlet plus reaction. So it's minus the change in the number of moles of A with respect to time. Okay? And so we have then nu AI is equal to nu times A0 plus K times V times the concentration of A at the outlet. Okay. I do this, I used to write it like this, and then I go to the bottom. But I have this for my undergraduate students. Okay? For you guys, it's probably easy to get there, but I do this for my undergraduate students, one step at a time. But you show then that actually the concentration of A at the outlet is equal to the concentration of A at the inlet divided by 1 plus K times V all over nu. And of course, V all over nu is equal to T. Okay? So actually, the concentration of A at the outlet is equal to concentration of A at the inlet divided by 1 plus kT. Okay? How do we test that this works well? What you do is you vary the volume flow rate, you measure the concentration of A at the outlet and that at the inlet, and determine, is K the same? And if it is, then this equation, or this relationship is correct. Okay? And so to test to see if their flow reactors or jet stirred reactors are working well, people do that to double check it. Okay? And they're sure that they're working well. Okay. So this was the variable pressure flow reactor here at Princeton University. Actually, I think it's moved now. It used to be Professor Dreyer's. Professor Law was there. He might be able to tell me, but I think it might have moved with him to South Carolina. Where is he? University of South Carolina, I think. You can check and see. But anyway, here it is. And it's a much different beast to, not a beast, I shouldn't say that, a much facility would be a better word. It's a much different facility to the jet stirred reactor that I showed you earlier. And actually, I use the word beast because it actually was a big piece, or is a big piece of metal. It probably would fit across the front of the stage here. The jet stirred reactor is quite small, right? You'd hold it in your hand, right? It's quite small. So it's a much bigger beast, this, compared to the jet stirred reactor. Okay, that's why I use the term. All right, but so, and again, it's made, and it's quite robust because again, you're working at 10 atmospheres or so. And then you have to have an overpressure because if you have transition to ignition or whatever, you're going to get an overpressure. So you want to protect, you don't want to kill grad students, essentially. You want to keep them alive, okay, and well. All right, so you have your gases coming in, you have an evaporator here, they're mixed here, and then they enter the reactor, okay? And so your gases start to react here, and then you have a sampling probe, and if you move the sampling probe up towards the entrance here, then there's very little time for a reaction. If you move the sampling probe right down near the exit here, you'll have the most time for reaction, okay? And again, you can tell you're going to have a volume flow rate, and then you'll have a distance down through the reactor, and that will then determine your time, the residence time of the gases in the reactor, okay? So, and that's how it works, okay? So, and there was an atmospheric pressure flow reactor here, and also a high pressure flow reactor. The atmospheric pressure one, I think the inlet moved. With the high pressure one, the sample probe moved, okay? Just two ways of doing it, but both are equally as good. So you can keep the sampling probe fixed and move the inlet, or keep the inlet fixed and move the sampling probe, one or the other, okay? Or maybe both if you want, but anyway. Okay, so again, for plug flow, it actually follows first order kinetics, okay? But again, we have the same equation. The change in number of moles of A, again, we're assuming A is reacting to give products, okay? And we have the change in number of moles of A with respect to time is equal to the rate constant times the number of moles of A. And that's equal to the rate constant times the volume times the concentration of A, okay? And again, but here we have the cylinder this time. And we have A at the inlet, A at the outlet. This is, the V is the volume of the reactor, and dV is a very small change in volume within the reactor. We'll come back to that in a second, okay? So we now have inflow is equal to outflow plus reaction, again. If nothing happens, then inflow is equal to outflow, or outflow is equal to inflow, okay? But assuming something happens, the outflow plus reaction is equal to what's going in, okay? And so we have the volume, the flow rate the flow rate times the concentration of A is equal to the flow rate times the concentration of A plus whatever change there is in the concentration of A, which will be a negative value, okay? Plus the change in number of moles, this is the reaction, Okay, so we have inflow is equal to outflow plus reaction. Is that all right with everybody? Okay. So at the inlet, the concentration of A is equal to the concentration of A at the inlet, and at the outlet it's defined as the concentration of A at the outlet. Okay, and we have so the volume flow rate times the concentration of A is equal to the volume flow rate times the concentration of A plus the volume flow rate times the change in concentration of A plus minus the change in number of moles with respect to time. Okay, so these cancel, and we then have minus the flow rate times the change in concentration of A is equal to minus the change in number of moles of A with respect to time in the reactor. Okay, now the reason that we write delta A is, is an infinite, we can actually follow infinitesimally small changes in the concentration of A in the reactor with infinitesimally small changes in volume in the reactor. If we do that, we can integrate across the whole reactor and determine what's happening in there. Okay, so that's what we're going to do. Okay, so we have minus volume flow rate times an infinitesimally small change in the concentration of A is equal to then, instead of using minus dNA dt, we use K times dV, an infinitesimally small change in volume, times the concentration of A. Okay, and now, so we now have this relationship, and now we're going to integrate, okay, across the whole reactor. Okay, so the integral of the change in concentration of A all over the concentration of A is equal to minus K all over nu, the integral of dV. Okay, I just rearranged the equation. And so if we solve this equation with the integral for the concentration of A at the inlet to the concentration of A at the outlet, the change in concentration of A all over the concentration of A is equal to minus K all over nu, the integral from zero volume to the total volume of the reactor, dV. Okay, so from the inlet to the outlet. Okay, so we have the log of the concentration of A at the outlet minus log of the concentration of A at the inlet is then equal to minus K times V all over nu. Okay, because the integral of dV is V. Okay, and so we have the concentration of A at the outlet is equal to the concentration of A at the inlet times the exponent of minus KT, because the volume divided by the volume flow rate is actually time. Okay, so we have the concentration, and this is essentially first order kinetics. It follows first order kinetics actually, and that's what comes out of it. Okay, so that's that. Okay, and here are data I'm very proud of. We published this in 1998 or 1999, I don't know. So these were data taken by Susan Fisher, was the student's name, and she worked here with Professor Dreyer in Princeton University, and I came to work with them, and we published this work. So she took this data at 5 to 1.19, a pressure of 12.5 atmospheres, and a constant time of 1.8 seconds. But again, the reactor, she determined that she had a volume divided by the volume flow rate and got determined the time from that. Okay, and then so she did a sweep again of temperatures measuring oxygen, the fuel dimethyl ether, formaldehyde, formic acid, CO, and water. And these are the profiles. Again, the points are the experimental results, and the lines are model predictions. And you see, again, these data place some strain on the model to reproduce the data in terms of all the different species as a function of temperature. Okay, so it's very valuable data that we can use to validate chemical kinetic models. Okay, but that was the model. I should have put the reference there to that, but we published that back in, I think, 1998 or 1999, sometime like that. Okay, we published 2 papers actually together. Okay, but this, I'm just showing this is the type of data that we can get from a flow reactor, okay? And again, that's very valuable data in validating the chemistry in the model. Can it accurately predict all those species that are being produced? If it is, it tells us, okay, the chemistry is well represented by the model, okay? Okay, I'm going to finish at that. So I'm going to start then talking about shock tube and RCM contribution to mechanism generation and validation. I'll pick up from that tomorrow, and maybe I'll pick up the pace a small bit as well, okay, so that we can get through it. But I hope that that was useful today in terms of all the background. What about, can I just ask, in terms of like introducing first order, second order kinetics, should I skip through it much quicker, or is it worthwhile doing it to that extent, or what do you think?